Okay, so we are continuing with the topic of single sideband modulations. Well, last time, please remember that last time we have discussed Hilbert transforms. And today, this is the application of Hilbert transform. Let me write it like HT. So this will be our first start to bandpass signal representation. So let's assume that we are sending a message M of t, through a communication medium. Maybe this is like a radio, AM radio or FM radio or something like that. So how do you transmit a message to the other side? So if you are transmitting a message wirelessly, you have a target in mind. Maybe you are transmitting to a nearby position, or maybe you are transmitting to another continent and so on. So let's assume that I am modulating this message by a center frequency, okay? And I select the center frequency such that, for example, I want to reach China, okay? Maybe this is Voice of Turkey radio, okay? There are radios like that, Voice of Turkey radio, and we are trying to reach China, very large distances. If that is your goal, then the center frequency is like 6 megahertz or something like that. For FM radio, for example, this is like 100 megahertz, 80 megahertz, something like this. So this frequency, as I have said, it depends on the, the range that you would like to reach and the propagation medium, obviously. So let's assume that now I have a message, maybe this is a song, okay, supposed to be transmitted after modulation to another location. So what is the case? Now, if I check this spectrum of this song, maybe I will see something like this. Let me sketch it a little better. So this is around 0 frequency, because it is nothing but, a microphone recording. A song is nothing but a microphone recording. So it's a voltage waveform. It's a real valued voltage waveform, okay? So let's say its magnitude response or the magnitude spectrum is this. Since this is just the message, not the filter, it's just the magnitude spectrum, okay, of this message. Now, if I, let's say, modulate it to the FC frequency, then what happens? Now, in the mid part, I have, again, something like this. And for the negative frequencies at minus FC, again, I have something like this, okay? And this is again covering exactly the same, let's say, bandwidth, 2 FM. For example, if this is like a, song or so on, this can be like a few, let's say, 30 kilohertz for the radio purposes, okay? Because that is the, bandwidth, let's say, plus minus 30 kilohertz is sufficient enough for the human hearing, okay? So this can be like 60 kilohertz bandwidth transmitted to a 6 megahertz center frequency. Now, this would be after modulation, M of t, let's say, modulated, okay? By the way, this is called amplitude modulation, AM modulation. AM, meaning that amplitude modulation. I think it's clear. Amplitude of the cosine is the message. Okay. So let me write then over here AM, because it's specific modulation over here. Now, in the spectrum, of course, there are some other radios. So the thing is, you want to use the spectrum efficiently. But there are some problems over here. What's that problem? Since my message is a real valued, a song, something like that, I know that there is some redundancy in the positive and negative frequency components. So what do I mean by that? So I know that since it's a real valued, it's a voltage waveform, then its magnitude spectrum is even, as you see over here, and phase spectrum is odd. Okay? Do you remember this? A real valued signal's Fourier transform is magnitude is even, as you see in the sketch, and phase spectrum will be odd. In other words, if I know this frequency, a positive frequency f1, I can exactly say what will be happening at minus f1. It will be having the same magnitude and its phase will be negative of it. Essentially, these values at these frequencies are complex conjugates of each other. Okay, that is it. So you see that the same thing will happen. So let's say f1 units away from carrier frequency 1, I have the same situation because it's nothing but it's a shifted version. Okay. Now you can see that I'm not using the spectrum very efficiently because half of this spectrum over here in this bandwidth, is sufficient to find the other half. Okay. Now one idea is to increase the efficiency. You can say that, okay, I'll be sending only this, right-hand side, this upper half. Okay. Or I'll be sending only this lower half. Okay. And then somehow, if I can reconstruct this signal, I'm done. Because you see that this upper half, this part, contains the same information as the whole signal. So that is the idea. So how can I do that? That will be the issue. So let me sketch this. So this is upper sideband. So this is a function of f. Upper sideband is, so let me extend this over here, So if I can do this, fc, I'll be having such a spectrum. So I'll be sending only this through this radio channel, only this part. This will be called upper means higher, sideband modulation. Okay. So again, this would be fc, and this would be maximum frequency. This is fm, so it's the same thing. So if I can transmit this through this radio channel, then there is some occupancy over here. Some other radio channel can also use this part, clearly, if I can manage to do this. So this is called, as you can see, single sideband modulation scheme number 1. So there is also another one, this is called lower sideband modulation. So as you can imagine, this is fc. This time we are selecting this part, lower sideband part, minus fc. Again, this is fm. Okay. So this is called, this is USB. This is lower sideband. Lower sideband LSB modulation. As I have said, this is due to spectral efficiency. Now I can use this part of the spectrum for another radio. Okay, that's good for our purposes. As you know, there are some auctions going on for the spectrum. So telephony or broadcast companies are paying lots of money for the allocation of the spectrum. So spectrum is a very valuable quantity. So I want to make this quantity, I want to make better use of this quantity by this kind of modulation schemes. Now the question is, how can I generate, such a signal? Okay, so that is the issue. Now let me write this. Upper sideband. This would be something like this. Let me see. And lower sideband, it would be something similar. Sine 2 pi fct. So now you may ask, what is this m hat? Well, this is the Hilbert transform that we have discussed. So this is the Hilbert transform of m of t as m hat of t. Okay, so if I take, this is my claim, if I take the Fourier transform of this, m USB of f, I should be getting this one. Okay, this is my claim. So we need to show this. Actually, the proof of this is right now available in your lecture notes, but I won't be giving this proof because at the end of this lecture, we'll be having a simpler proof for this. But you can also, by taking directly the Fourier transform of this, okay, you can see that I'll be getting a spectrum which is 0 from here to there. Okay. So this spectrum will be 0 in this part, meaning that this part is eliminated. Okay. But let's postpone that proof for your personal study at home. You can check that Fourier transform calculation. But let's go ahead and study something more general. This is bandpass signal representation, and this is actually the main topic of today, bandpass signal representation. Now, a bandpass signal, occupies a bandwidth from, let's say, f1 to f2 in spectrum, and let's say 0, and it's not, let's say, let me write it, DC frequency is not in the bandwidth of the signal. So what do I mean by this? Well, here is this. Now, if I have, let me see, g of t, this is the bandpass real valued signal. Okay. So if I sketch g of f in magnitude, so this is, let me look at my sketch, something like this. It starts from f1, let's say, it goes to f2, something like this. So since this is real valued, again, so I have the same situation, meaning that the magnitude is an even function over here. So let's say that this peak value is also a, for the sake of clarity. Okay. So this is a bandpass signal. Now I would like to represent this signal, the information content of this signal, without any redundancy if possible. So how can I represent it like we did over this one? Okay. Over here. So our goal is to represent bandpass signals, or let me write real valued, because it's something very practical, real valued bandpass signals as, let me say, low pass, or signals with their low pass equivalent. With their low pass equivalent. But low pass equivalent will be, complex valued. Okay. Valued. I had this. So let me see, what do I mean by that? Again, actually this is a bandpass signal, but all the information content is actually over here. I don't care about what is going on elsewhere, isn't it? So let me call this my bandwidth. So BW, okay. So this, of course, real valued. The same bandwidth also appears over here. But I don't care about anything else. Somehow, if I can represent this part, I'm done. So first topic is, now topic number one. So I want to discuss bandpass signal to low pass equivalent let's say low pass equivalent signal. So this will be our first topic. How can I find the low pass equivalent of a bandpass signal? Okay, that will be our topic number one. So this was quite easy, but it has two steps. Step number one, find, it's called something else, I will explain, analytic slash pre-envelope. Let me write signal. So what do I mean by this? G plus of t. Okay. G plus of t is G of t plus J. Let me write better this. So this is called analytic signal, or as I have said, pre-envelope. It's the same. Now you may wonder, actually something like this, as you see. G and G hats, but of course different. I mean, it's not exactly the same. So analytic signal is defined like this. Okay. So let's accept this definition. And let's just calculate the Fourier transform of this. Maybe we can see what's going on. Okay. Now this is G of f, this thing, plus J times this other function in Fourier domain. What is this other function in Fourier domain? So this is the Hilbert transform. So what was the Hilbert transform? Minus J signum f times G of f. Am I right? So then let me use this part. So you see that Hilbert transform will be very handy in such calculations, because you will see there will be an interesting cancellations in the Fourier spectrum. Okay. So where were we? We were at this point. Now there are two G of f's over here. Let me pull them in the common bracket. So let me write it like this then. G plus of f is equal to G of f times 1 plus J times minus J, 1, signum f. So what's going on? It's a little interesting. 1 plus this. So this is actually equal to when frequency is greater than 0, because signum function is piecewise defined. So when f is greater than 0, this is 1. 2 times G of f. When f is less than 0, this is minus 1. So this is identically equal to 0. So what do I have as a sketch? So this would be the Fourier spectrum of the analytic signal. Am I right? So it's only this part. Okay, only the positive part. This part. So from f1 to f2, I have something like this, and something like this. All the differences, maybe I should be a little bit careful. Multiplication by 2. I mean, it's not a big deal, but in terms of exactness, I have to have that. Okay, 2a. So do you think it's actually we are approaching our goal? What was our goal? I would like to capture this part of the spectrum. Am I right? I would like to capture this signal somehow. This triangle and like curve shaped signal over here in the spectrum. I would like to capture this. Now in step number 2, as you can imagine, now shift the analytic signal to DC frequency. So, and get low-pass equivalent. Low-pass equivalent signal. So do you see what I mean? I'll be shifting this to the origin, meaning that this is the frequency, and then that will be our, low-pass equivalent signal. That I'll be achieving my goal. So then low-pass equivalent signal is in time domain. So I have this analytic signal, this thing, in time domain, shifted to DC frequency. But how can I shift this to DC frequency? Well, I can select any, let's say, frequency over here, but let's say that I'm selecting this my FC, somewhere in the middle. It doesn't have to be this peak point. I can select any point you will see. Okay, let's select that one. This peak point for the sake of drawing, just FC. Now I will, just for the sake of drawing, I'll be doing this. Now obviously, if I do this, the Fourier transform of this, F plus FC, am I right? So clearly this FC is positive, because in the positive, let's say, line segment, so this is shifting towards the negative frequencies, you know, things like that. So I have this. So if I sketch this right now, Lowpass equivalent as a function of, in the Fourier domain, as a function of frequency. Now shift this to over here. So this is minus F1, this is F2, let's say curve like this, and it's like 2A. That is it. Okay. So as I have said at the beginning, my goal is capturing this signal, because this is the information bearing signal. If this is like, let's say, the radio message, then I'm interested in this message. I'm not interested in what's going on anywhere else. Okay? Yes?
Isn't that F2 minus FC?
Which one?
Limits.
Huh?
Limitler, yani F2 eksi FC.
So if this is FC, I shift it by FC to this unit, then this becomes minus F1. Okay? And oh yes, definitely. If you are calling this, so let me write it like 0 over here, then this would be, you are talking about this, isn't it? F2 minus F1. Okay? Over here, F2 minus F1, that is the bandwidth. F2 minus F1 is the same bandwidth. You are definitely correct. Okay? So this is the range. Okay, so this is the first topic, bandpass signal to the low-pass equivalent. So what was the trick? The trick was, you know, this analytic signal. Okay. So once I construct this analytic signal, essentially this picture, the rest was quite easy because I have eliminating everything else and I'm just limited by that. Okay. So the second topic is, let me see, the reverse operation. But before that I should write some notes. Okay, let me write some notes. Number one, low-pass equivalent signal this is GLP of T is a complex valued signal. Let me write it over here. Well, why do I say so? Well, the original signal is, this is clearly real valued because on the spectrum it has this kind of an even symmetry. But if you check this doesn't have even symmetry anymore. Okay? This is a complex valued signal. Now in signal processing courses, students always ask, why are we dealing with these negative frequencies? You know, what's the meaning of negative frequency and so on? Well, you see that the negative frequencies are needed / used to express, as you see, low-pass equivalence of bandpass signals. Do you see what I mean? Because at the end, after this operation, you are getting a complex valued signal. But this complex valued signal is representing the actual bandpass signal. So that is the reason that we are studying, you know, this frequency axis starting from minus infinity going to infinity. But in some textbooks, you can see that even these sketches are starting from 0 frequency and going to the positive frequency because they're always focused on real value signals. Okay? Our focus can be, as you see, the complex valued case also. So number 2, comment number 2, let's keep that. Comment note number 2, the FC frequency is called the carrier frequency. Does not have to be at the center of bandwidth of the bandpass signal. It can be at anywhere, including outside of the bandwidth. Okay? Because this argument does not depend on the selection of FC. FC can be over here, then this point will be, if FC is over here, then this point will be moved to the DC frequency. Do you see what I mean? It doesn't matter. Again, you have a complex valued signal. So for the sake of drawing, I have just mentioned this. And that is it. FC doesn't have to be at a special location. It can even be outside of this bandwidth. Then I'll be, after this shift operation to the zero frequency, this will be totally at the negative part. Okay? At the negative frequency part. That is it. So 2 nodes. That's our conclusions for the bandpass signal representation as a low-pass equivalent. Now the reverse topic number 2. So this one will be, now given that low-pass equivalent signal, now I'm given this. So how can I construct bandpass signal? Okay. So this is our topic number 2. So what's the problem? Given low-pass equivalent signal, the reverse operation as you see, and let me write over here, and an FC frequency, how to construct the bandpass signal G of t. Okay, that's our question. So what can be our answer? Our answer is actually quite simple. So do the reverse operations, not reverse, but do the operations in topic number 1 in reverse. Do you agree? I mean, simple idea. So if I know this, okay, somebody has given me this, then shift this to this part and then duplicate it if possible. Okay? Then I'll be getting my, the bandpass signal. So how can I do that? Let's again sketch this. So how can I handle this one? Now I'm starting from the low-pass equivalent signal. It is something like this. This is F2 minus F1. Okay. So the reverse operation. I should get this one. Step number 1. Then I will get the analytic signal. Analytic signal in Fourier domain. Okay. So there is an FC stated, given to me. So this is this. This is this. Again, let me write bandwidth for this one. Bandwidth. Okay. So what's the next step? Then the next step is construct G of F. Well, which one is this? Is flat. Again, this is the bandwidth. This is the bandwidth, and so on. Okay. So how can I do this? Well, again, let's be careful because this is like 2A. This is like 2A, am I right? But at the beginning we have started with, you know, A. Something like that. I should get reverse operations, something like that. So how can I do this? So let me get this one. So G, so let me say algebraically. So this is graphically. Okay, this is what I'm trying to achieve. So algebraically, I should do something like this. Analytic signal is this thing shifted to the right this time. Low pass equivalent signal. Am I right? Shifted to the right because, I mean, move this to this side. If you move this to the other side, this is equal to this. But I think it's better to remember from here, this picture. So I have the low pass equivalent signal, moved to the carrier frequency. This becomes the analytic signal after frequency modulation. Now, how can I get this one? Well, let's remember, this was G analytic signal. G plus of t is equal to G of t plus J, G head of t. Am I right? So in the second step, this part, so I will just do the following then. G of t is equal to real part of, because you see, real part of this thing, G plus of t. In other words, this is the real part of low pass equivalent signal that you know, this is given to us, modulated to the carrier frequency. I get a complex valued, let's say, signal over here, and I look at the real part. The real part will be giving me G of t, okay? The reverse operations. So that is the end. That is the topic number 2. But I would like to say one more thing. Let me find the eraser. Now, we have said that the low pass equivalent signal is complex valued. So let me define the following. Gi of t plus j gq of t. Because we have said in note number 1, this, I have just erased this one, okay, before this one. This is a complex valued signal, the low pass equivalent. And this is its real part. So Gi of t is obviously the real part of this, and this is the imaginary part. Gq of t is imaginary part of this. Okay. Now I'm talking about this in time domain. Complex valued in time domain. Real part is Gi, Gq, and I will call this in-phase component, and I will call this quadrature phase component. In-phase component. This is called quadrature phase component. Okay. Okay. Then G of t is, one more time, writing this. Low pass equivalent modulated to the carrier frequency and taking the real part. G of t is low pass equivalent modulated to the carrier frequency, taking the real part. So if I substitute this, because I don't want to deal with this real part operation, let's evaluate this in terms of Gi and Gq. Okay? So you will get real times real. Am I right? Real part times real part minus imaginary part times the imaginary part of this. Okay? So what is this? Now this is actually quite important for our purposes. please remember, this is our bandpass. Bandpass signal. And these are the in-phase / quadrature Q, quadrature phase, let's say components or parts of low-pass equivalent signal, in-phase, quadrature phase. Okay. IQ, sometimes we say it like IQ pair. Okay. So that is it. So this is the carrier frequency. FC is the chosen carrier frequency for this calculation. Okay. Now, topic number 1 was, it was this. Given G of t, how can I find low-pass equivalent? Or equivalently, how can I find GI and GQ? Low-pass equivalent is something like that. So given this G of t, what do? We calculate the analytic signal. Analytic signal is, let me see, it is this. So left side of the spectrum is totally nulled. Then you move it to the right, and then that becomes a low-pass equivalent. Now from the low-pass equivalent, it's topic number 2. How can you get back the original bandpass signal? So from the low-pass equivalent, do the reverse operations. Given the low-pass equivalent, modulate it to the carrier frequency, and then take the real part of the signal in time domain. Okay? You get this done. So this is the basis of all kinds of communications, digital communications, radio communications, analog communications, etc. Because this is essentially the bandpass signal representation. Okay. So all bandpass signals are represented like this. And this equation is called canonical representation of bandpass signals. Okay? So sometimes we will be mentioning this canonical representation of bandpass signals. Okay, so let's have some examples. But I want to keep this, at least this one, for future use. Not to erase it, let me reserve this space. Okay, so let me see. Our example is the following. G of t is, what was this? Cosine 2 pi, there is no amplitude, cosine 2 pi f naught t. Okay? And question is, find G low-pass equivalent with, let's say, Fc is equal to F naught. Okay? So let's say that this is question number 1. So how can I do this? Well, let's draw the graphs. So this will be graphical solution. Actually, this is quite important because this requires some understanding of what is going on. Now, what is G of f? 2 impulses in the spectrum, am I right? Because of this cosine. Okay. What is the next step? The next step is, let me do it this way. Now you say that I'll be finding the analytic signal spectrum. So what is the analytic signal spectrum? This part is nulled. Okay. So whatever I have over here, positive frequencies, will be multiplied by 2. But since there is only this, F naught, this is the analytic signal. Okay. So what's the next step? We are almost there. Low-pass equivalent. G low-pass equivalent in Fourier domain. I think you really enjoy the Fourier transform properties at this moment, isn't it? Shift property, linearity, those kinds of things. Because this is nothing but, application of those simple properties, modulation property, etc. Now it says that find the low-pass equivalent. This is the point where I need this carrier frequency. Okay. So because I'll be shifting the spectrum to the left by the amount of carrier frequency. So what's carrier frequency? Carrier frequency happens to match this. So let me write also here. This is also FC. Okay. Then if I shift this over here, I get this. Always 0. This. So how about in time domain? So inverse Fourier transform of this is just constant 1. So this is the end of this case then, okay? Because it was find this with this. So story is in 2 steps. So information bearing part is this part, wherever it is, because this is redundant. So I first null this part, then shift this, make it low pass, okay? Low pass signal. That is the whole story. So how about this? From canonical representation. So let me copy this canonical representation. This is always valid. Let's say that I don't do this sketch. I start from this canonical representation. Okay. Forget about this graphical part. The problem is g of t is this. So this is an arbitrary bandpass signal. So right now in my example, this is equal to, fc is equal to f naught. Let me write f naught, but this is also equal to fc. Okay? Now the question is, if this is this one, meaning that this is also equal to fc, can you find this and that such that I have equality for all t? Okay. So what do you think? Now it becomes trivial, isn't it? Because if this is equal to 1, I have this is equal to 1 times cosine. This is equal to 0, and we are done. So from the canonical representation, we get the same result. It should be like that. Then gi of t should be equal to 1. gq of t, quadrature phase component, should be equal to 0. Okay? Then, low-pass equivalent in phase, the real part, plus j quadrature phase, the imaginary part, is equal to 1. Yes. It should be matching that, obviously. Otherwise, we are in trouble, isn't it? Okay, so let's solve the same thing. In a different way. Problem number 2. Repeat 1 with, let's say, carrier frequency is f naught plus delta f. Okay, I will explain. Delta f is a positive quantity, but delta f is a small in comparison with f naught. Okay. Maybe you don't know the exact value of f naught. Okay, maybe because this is not your radio system, maybe you are just guessing this. This is the center frequency and so on. So you are just modulating it, trying to find its low-pass equivalent. So again, let's do it graphically. Same story. F naught minus F naught, 1/2. This exactly the same. Exactly the same. But as you see from here to there, I multiply by 2. Okay, now there is a change. So this is F naught. So my carrier frequency is somewhere over here, Fc. Meaning that there is delta F hertz in between. Okay. So Fc is this value plus, maybe if this is like 1 hertz, F dot plus 1 is equal to Fc. Now, if I this next step. Now, if I let's say shift to the DC frequency by the Fc amount, what do I get? So I get minus F naught, and this is equal to 1. Am I right? So this will be our low pass equivalent in frequency domain. Let's say these are the magnitudes, let's say. Sorry, you are definitely correct. This should be minus delta F. Definitely, you are definitely correct. Minus delta F. Okay. So, how about in time domain? So this would be equal to, this time, e to the j 2 pi delta f with a minus sign t. Am I right? So this is the inverse Fourier transform. Inverse Fourier transform of this. So in other words, this would be cosine 2 pi delta ft minus j sine 2 pi delta f t over here. And you can see that this is the in phase. Let me write over here, in phase component. And this is, well, minus sign is over here, this minus, because this should be, minus sign should be over there. Minus quadrature phase is sine. Quadrature phase is minus sine. Okay, that is it. Again, can we find this from the canonical representation? Well, let's give it a try. From canonical representation. So how can I do this? Now I should be writing the same thing for over here. So this time only difference is, let me write, g of t is this time something like this, cosine 2 pi f naught t. Am I right? Okay. So this f naught is equal to fc minus delta f. F naught is equal to fc minus delta f. Do you agree? Then how about this cosine expansion? Cosine a minus b. Okay. I will use this cosine expansion. So if I use that, let me use this part. Cosine 2 pi delta ft cosine 2 pi fct plus sine 2 pi delta ft sine 2 pi fct. Okay? Because this will be at the end a minus b. So a is this, b is this, and so on. That is it. So then, if gt is like that, so how about this if I compare with this? If I compare this gt with this canonical representation, this one, let's say. So how can I find gi and gq? So this is supposed to be then no other way around. gi of t. And this is supposed to be minus gq of t, because minus gq of t is the factor of sine. And minus gq of t, well, very nice, I'm very happy. Minus gq of t is indeed sine, and this is equal to this. Again, it matches. Okay, good news. So right now we have seen how to calculate this low pass equivalence. Now one more thing, and we will be covering today's topics. I just want to come back to this eventually. So let's also erase this. Okay, so let's keep this. This is our canonical representation. Now, also, from practical viewpoint, so let's see. I want to discuss two things. They are both simple, very simple. I'll be just drawing block diagrams. Generation of bandpass signals. So what is this topic? Now, given in-phase component somehow and GQ and FC generate G of t. Well, how can I do this in practice? Now this will be in phase. I'll explain this. So this oscillator, let's assume that it generates a cosine with this frequency, cosine 2 pi fct. So there is this phase shifter by 90 degrees, and this part becomes sine 2 pi fct. Okay. So whatever this phase is, subtract 90 degrees, cosine becomes sine. That is it. Now, given this, and that, and FC, I can construct this. So what do I mean by I can construct this? This is just, if it's a voltage waveform, you are multiplying a voltage waveform by a cosine. You are multiplying another waveform by a sine. Okay? So you delay this oscillator by a quarter of a phase. Okay? Then you have that. So if you add them up in this way, plus minus, I'm claiming that this will be our bandpass signal. So how can this be? Well, actually, if you check this canonical representation, it's exactly this one. Gi times cosine minus gq times sine. This minus is over here. Gq times sine. Okay? Let me put arrow over here. Okay? Gi times cosine. That is it. So this becomes a practical implementation, as you see. For example, you are singing a song, recording it on your microphone, and then putting it over here. Then maybe there is nothing over there, 0. Then this would be, do you remember, m of t times cosine. Song times cosine. Okay. How about upper sideband? For the upper sideband case, then you will be doing the following. M of t is over here. It's Hilbert transform. M hat will be over there. So then this will be a bandpass signal, but what kind of a bandpass signal? Upper sideband. Okay? That will be an upper sideband signal. If you think about it, then the low-pass equivalent of something like this, G of t is m of t plus j m hat of t. Am I right? So this is low-pass equivalent for the upper sideband case. So this becomes Gi of t. This is Gq of t. And if you check the Fourier transform of this low-pass equivalent of this one, this will be exactly upper sideband case. Because again, these negative frequencies will be nulled. Okay? Okay, this is just a note. This is the thing that we didn't prove. Do you remember I was telling at the beginning of this hour? I was saying that, okay, we can prove this by Fourier transforms, but we don't need to prove it by Fourier transforms. Now we have studied this bandpass signal representation. So I know that if I have a low-pass equivalent like that, it will be something like this with negative frequencies all 0. So if you shift this, clearly this is upper sideband. Okay? That is it. Now the second topic is also very similar. Now generation of, this time IQ signals, in phase and quadrature phase signals from bandpass signals. By the way, this topic is called demodulation. This topic is called modulation because this can be, as I have said, AM radio and so on. Okay, so you are, it can be different than that. It can be other modulations. Now, how about the demodulation? In demodulation, the problem is given this time G of t and Fc, we want to find, let's say, get in phase component and quadrature phase component. Okay. So there will be a similar block diagram. Again, we will be making use of this canonical representation. So this is, let me have something starting over here. Let me see. So this is the same oscillator. So let me write cosine 2 pi fct. But there are little differences. So low pass filter, its output will be, let's say, x of t. This is y of t. So this will be in phase related. I'll explain. This will be quadrature phase related. Again, this looks again complicated, but the main idea is making use of this canonical representation. So this is the critical thing, canonical representation. Okay. So what's going on? Now, let's try to figure out what this output is. Let me call this part x prime of t. So x prime of t is nothing but g of t times this cosine, isn't it? Similarly, I can call this y prime of t. So this is plus 90 degrees, as you see. So this becomes minus sine 2 pi fct. So there is a minus over here, because this is, let me, plus. Because of this, I have a minus sign. But I'm not dealing with y prime right now. I'm dealing with x prime. Then let me substitute this gt from this one. I'm hoping that I will get in phase component at the end. So this is in phase component, cosine square 2 pi fct, okay, minus gq sine 2 pi fct cosine 2 pi fct, and that is it. Okay. So there is a low pass filter over here. Now if you check this, this is sine times cosine. This would be equal to sine 4 pi fct, because this is double angle formulas for the sine expansion. It's something like that. How about this one? This would be again double angle formula. So this would be 1 plus cosine 4 pi fct. That part. So what do I have? I have gi of t divided by 2 plus, if I write over here, high frequency terms. Do you see what I mean? Because all other terms has the double carrier frequency. Okay? So all other terms, there's 1 over 2 times this, but this one is multiplied by a very high frequency sign. Gi of t is multiplied also by this very high frequency cosine, and so on. So low pass filter will be eliminating this, then this would be, at the end, as you see, I'll be getting this part at the end of my filtering. So this is the reason that I call this in-phase related. It's not exactly the in-phase signal. There's 1 over 2 factor, okay. I can adjust that, but there is also filtering effect of these high frequency terms. They may leak into this type of system. But in practice, since this carrier frequency is very high, and the bandwidth of the message is very small in terms of carrier frequencies, that leakage will be very small. Now you can see that this demodulator, this practice, works quite well, okay? So if you have a bandpass signal, this bandpass signal, then you have an oscillator demodulating it to the IQ signals. Okay, and these are called in practice, in hardware practice, IQ channels of this receiver. Of course, there are issues, like this should be exactly 90 degrees and so on, isn't it? Otherwise, this cancellation, double frequencies will not be happening. So you have to be very careful about that. There are some other practical details, but this is basically it. So if you check this one, this is more like a radio transmitter this time. So as I have said, maybe I'm just recording my song and placing it over here. This is 0. Pass it through this one. This becomes m of t times cosine, but it's not spectrum efficient. As you see, if I include it over here, Hilbert transform of that, it becomes upper sideband modulated, single sideband, okay, modulation, and so on. So there can be different modulation schemes. This is a topic of telecommunications actually, how you come up with different communication schemes for different purposes, okay, for different operational conditions. Maybe your channel is very noisy, maybe you are sending analog signals, maybe you are sending digital television signals with large bandwidth, and so on. It depends on so many other things. Maybe there are multiple users, single users, distance, propagation effects. So it's a big deal, but these are the essence of receivers and transmitters in communications. Okay, that's all for today. So we will continue next week with more lectures.